Maggie did a really excellent job highlighting all of the field work that we've been doing and some of the data sets that I haven't even seen them yet, so I'm really excited to see what's coming out of these. And what I wanted to do is take a bit of a step back and talk about the system as a whole and our rationale for why we're doing this work. So especially digging into the role of ionic composition and concentration in these environments. And I just wanted to say thank you to my co-Is, Chris Carr and Maggie Osborne. Also, we have collaborators Shuei Ono, Virginia Walker, and Jack Shostak. So the inspiration for this project actually came from DHABs, deep hypersaline anoxic brines. And there were two specific papers, which you haven't read, I think you should, that were looking at ATP and DNA preservation in these hypersaline anoxic brines. And the interesting thing is that DNA can potentially be formed, can potentially maintain its conformationally active. So that was really interesting, and I wanted to delve into what is it about these salts and why some salts are better than others at doing this. So some definitions. First off, water activity. I'm sure a lot of us are familiar with it, but I just want to go over it a little bit. Thermodynamic availability of water. So pure water has an AW of 1, and the limits of life are currently around 0.605. This is zero-tolerant fungi that can grow off of sucrose solutions. But different salts affect this differently. So magnesium sulfate at saturation has a water activity of 0.86, but magnesium chloride at saturation has a water activity down around 0.33. So these two salts obviously have very different solubilities, and their ion pairing is really affecting how water activity is determined in the system. And the thing that I want to drive home and something to think about going forward is that we usually use water activity as the metric for habitability, but it's really important to understand that these values aren't all equally habitable. So NaCl system at 0.67 is habitable, MgCl2 system at the same water activity is not. And that has to do with these ions in the Hofmeister series. This is actually not anything new. This is published first in 1888. It's a little bit complicated to just look at the anions on the bottom. These are ordered from cosmotropic, which are stabilizing, to chaotropic, destabilizing. And this is both for how they affect the structure of water and differing biological molecules, specifically proteins and lipids. So these cosmotropes here can salt out proteins in solution, and so but they'll do an opposite thing for DNA, whereas these are going to destabilize proteins in solution. The cations get even more complicated. This is ordered with respect to their effects on water, but you have to flip it with their for their effects on biological molecules, and it depends on what biological molecule you're talking about. So it's really complicated, and it's not well understood. And the reason that we're specifically looking at magnesium sulfate environments is because we've got that interesting dichotomy between. We've got this interesting dichotomy between this cosmotropic anion and this potentially chaotropic for biology cation. So that's why we're looking at magnesium sulfate. There's also an extensive evidence for the salt on Mars. But this salt is not highly common on Earth, and the majority of system studies are NaCl. So as Maggie said, we're looking at these 3 lakes in the middle of nowhere, BC. It is fantastic. You should definitely go. The reason that these lakes are here is because they're located between the Cascades and the Rocky Mountains, so we're in a rain shadow. Things are really, really dry in this environment. These are glacial basin lakes, glacially formed basin lakes, closed basin, and so that's why we're getting a huge concentration within the environment. So we've already looked at these a little bit. As Maggie pointed out, these are spotted lakes, which are unique to this part of the world. We don't know about them anywhere else, and we don't know why they're doing this. So that's another question that's outstanding. This crazy map is the geology of the area and why we have some really unique ions in solution. So basically, Last Chance Lake is underlain by basaltic volcanic rocks, and whereas Lake Clinton and the Basque Lakes are underlined by marine sedimentary rocks. And then I should also point out that we've got granodioritic inclusions throughout the region. This whole gray unit here is Permian to Upper Triassic limestone marble, which is why we're having we have a lot of magnesium carbonate in the environment. And there's also pyrite and pyrrhotite deposits, which is where our sulfuric acid is coming from. So a little bit more about these spotted lakes. They're spatially stable over time. So this image here was taken in 2016, and if you compare it to the 1918 paper, the spots are in the same place, so they're not moving. We don't know what's going on in this environment. They never really dry out enough to really be able to dig down, and it's also really difficult to core in this environment because there's a hard layer of salt about 30 centimeters down that you just smack into. So we don't know what the hydrogeological controls are, and I've been chatting with Jill actually this week about maybe trying to do some resistivity here to get a handle on what the hydrology is of this environment. So as Maggie touched on a little bit, we want to constrain the physical chemistry of this environment and assess ion-specific effects. And that's why we're looking at both a sodium sulfate lake and magnesium sulfate lake and the difference that these two cations have on biological stability. I want to look at characterizing the community, of course, and then assess this preservation potential, looking in the salts, the sediment, the water column, and also doing these sediment cores and looking at it across time. And we're looking at sort of short-term biosignatures, such as ATP and DNA, and longer-term biosignatures, such as these lipids, IPL versus core. We're looking at amino acid racemization, and also I'm interested in sulfur fractionation at high salinities in this environment, for which there is a lot. So Clinton Lake, this is us coring for the first time. Many thanks to Yarrow Axford for showing us how to do it. You might note that the core head is above the water. This is really difficult to do. And your boards float when it's really, they float anyway, but when the brines are this dense, they really float away. We got it back, but this was a challenging environment to work in. And they're supposed to be dry. This is the dry season. I'll note that there's 8 centimeters of water on top of this lake, and so to get out to the spots, we had to do this. But there was still coherent subaqueous salt about 20 centimeters below the surface. That was really neat. Basque Lake number 2 is in a much drier location, so we could get to those pools, which was fantastic. We had hydrogen sulfide bubbling up underneath the salt crust and forming iron sulfides. And if you pull that out, you can see photosynthetic layers and then also your black anoxic layer right here. Also, there's these great little brine shrimp that were only in pools that had a water activity above 0.9. So in our really shallow pools, they didn't exist, and we just found brine shrimp eggs. And then finally, Last Chance Lake, which is our sodium sulfate. That chemistry is wrong, but it's okay. We didn't have salt precipitating in the lake here, and we think that's because it's much more soluble salt, and the only places we got it were on trees and branches that were along the margins. Again, this was supposed to be completely dry, so it wasn't ideal, but we still got some really interesting data. So this is ICP-IC data from the fall. We've got concentration millimolar here and salinity in grams per liter on the on the y-axis. And then the different lakes, so Salt Lake and Last Chance were flooded, so we only have one data point, but we got the 3 different pools for Basque Lake. And you can see the water activity data here below. So I'll highlight the fact that Salt Lake and Last Chance, because they were flooded, had fairly low salinities. Salinity for Salt Lake was 90 grams per liter, and then we were at 160 grams per liter. And then I'd like to draw your attention to this. I said it was sodium sulfate. The literature says it's sodium sulfate, and it was most definitely not sodium sulfate when we sampled. So there's something really interesting going on there. It might be a temporal variation that occurs when you have a huge rain event. So we're going to have to go back and sample a few times to figure out what's going on here. But we did get some really nice salinities here at above 300 grams per liter salinity. So this stuff was maple syrup at this point. As Maggie mentioned, we're taking sediment cores from all of these environments so that we can sample down core and look at degradation of all of these various biomolecules of interest. So the cores from Lake Clinton and Basque Lake number 2 are pretty good. They have sedimentation rates of 0.01 centimeters per year, so pretty low, but pretty good correlation. We have a couple of age inversions here. This is probably us kicking up the top layer of sediment because it was really hard to not disturb the area. We're checking on hard water effects. And as you can see, Chris here trying desperately to get this core into the ground. This is where there was this hard layer of salt underneath, and it was impossible to get through, so we're working on that. Last Chance Lake is really weird. We don't quite know what's going on here. We have a lot of age inversions within the down core. So these two are outside of the circle here of the pond. And then these two here are within the pond. So this should say core D, by the way. So this purple line here is core D. You can see that we have age inversions all over the place. But then core C, which was a little bit more towards the center of the pond, is actually not too bad. So what was interesting is with Last Chance Lake is that we actually get sorting in these ponds, which you don't see with the other ones. So the freeze thaw may have an effect in why these ponds are forming, but we don't see it in Basque Lake or Salt Lake. But in Last Chance Lake, it might be happening, and that may be why we have all these age inversions here, because we're getting turnover of the substrate when we get freeze thaw action each winter. And again, we went back in the winter in February. It was minus 30 Celsius. That was a new one for me to work in constantly, but it was fantastic. And we got some drone imagery, and we're going to go back this fall and get some drone and hopefully some spectral imaging of the sites. We do have some ATP brine data from the winter months. The summer we had to figure out how to do this because they're so saline that they were causing saturation of the detector and inactivation of the luciferase enzyme. So you can see here that we have, for Clinton Lake, we had water at 3 different sites moving outwards from the shore. So this is closest to the shore, and this is closest to the center of the lake. So you can see that free ATP is increasing, but our cellular ATP is sort of staying a bit level. It's not necessarily correlated with that. With Last Chance Lake, we have, this was the first 2 drill spots, the ice had frozen to the bed, but right out into the third spot, we got brine finally, and we could sample that. So we had fairly high levels. And then same with Basque Lake, the 2 ponds that we had sampled in the summer had frozen directly to the bed. And so Basque Lake 2.3, which originally had that high water activity and had the brine shrimp in it, that was what we were looking at with our ATP, and we had very high cellular ATP in this environment, which may be reflective of those higher water activities. I wish I had cell data to compare this to for you, and it's coming imminently, but we couldn't get it in time for today, unfortunately. And then just to follow up from that, we did look at the ices, and there's not really a strong correlation with distance from the shore. LCL is constant across the 3 different sites, and then we have a lot of variation in BL in Basque Lake 2, and we don't know why that is, so it's still something we're looking into. So to finish up, the salinity in the lakes range from 80 grams per liter to 300 grams per liter with water activities down to saturation for the brine. The sediment ages date back as far as 6,000 years for Salt Lake, 5,000 for Last Chance, and 3,400 for Basque Lake number 2. We're going to be recollecting ATP data along this with this year and looking at, we're really curious about whether or not ATP is being concentrated within these cells, because that happens a lot in, say, hypersaline environments to be used as a biological cosmotrope. And so trying to get at this idea of like, are ATP values representative of cellular, of microbial activity and microbial biomass in these environments, or is it an artifact and you're going to get really high values because it's being preserved? Sequencing is currently underway, and we're also back in the lab conducting empirical tests. So we've created magnesium sulfate, sodium chloride, and magnesium chloride brines at a range of different concentrations. And we're doing incubations of DNA, plasmid, ATP molecules, and we'll be selecting some IPL to do incubation experiments to look at what the empirical rates of degradation are, and to compare that to what we're seeing in our sites. So just wanted to say thank you to the NASA Exobiology Fund for funding this work. Jacob Buffo, Mario Tubas Rodrigo, Peter Doran, Hannah, Dan Kirshner, Yarrow Axford, Quinn Gavagas is like the best veterinarian ever and gave us our LN2 in the field. Richard Feynman, and then the Caribou Lodge staff, which is very key in providing that ladle and letting us get down to the sediment underneath the ice. So thank you very much for sticking it out for Friday, and I'll take your questions.
All right, we have time for one quick question. All right, I have one actually. In your conclusion, maybe I'm misunderstood, but I thought that cosmotrope were like the effect of salt or anions/cations on proteins. So I'm a bit confused how ATP could be a molecule being a cosmotrope.
Like different types of molecules can also be cosmotropes and can also act to stabilize or destabilize potentially. So it's possibility that ATP is being concentrated in cells in that manner. There's a paper that I think came out in 2017 that talks about this as ATP as a biological heterotrope, I think is the paper. And so you can look at that to get into that a little bit more.
Thanks again for our speaker.